For the last half century, the story of computing has been, well, pretty simple. It's been a story about one thing: shrinking, making things smaller and smaller to make them faster and more powerful. But that story, it's changing. Today, we're going to dive into the fundamental reinvention of the computer chip and what that really means for the future of our technology.
Think about it. For decades, we've all counted on this one predictable, exponential rhythm to power our entire digital world. But what happens when that rhythm falters? When the very foundation of how we make tech better hits a physical wall? Well, that's the massive challenge the whole tech industry is staring down right now.
The rule was just so beautifully simple and reliable. Just shrink the components on a chip. More transistors crammed into the same space meant more power for less money. But we've finally reached a point where we're hitting the hard limits of physics. You just can't shrink them much more. So yeah, that reliable old playbook, it's officially closed. And this observation, Moore's Law, has been the engine behind the entire digital revolution. It is the reason your smartphone is ridiculously more powerful than a supercomputer from just a few decades ago. But with that engine slowing down, engineers have had to get incredibly creative. They're not just shrinking anymore. They are rethinking everything, starting from the most basic fundamental level. So if you can't just shrink the switch anymore, what do? Well, you reinvent it. And that's the first major shift we're seeing. It's happening with the most fundamental component of any chip: the transistor itself.
Okay, so what's really cool here is the change in the actual shape. For about the last decade, we've been using what's called a FinFET transistor. You can see the gate, which is kind of like a light switch. It controls the flow of electricity from three sides. But the new design, called Gate-All-Around, or GAA, it's a huge leap. As you can see, the gate literally wraps around and hugs the channel from all four sides. And this brilliant little design tweak has some incredible benefits. That four-sided control gives you so much more precision. It means less electricity is wasted leaking out, which in turn lets the chip run on a lower voltage, and that saves a ton of power. It's really the key that unlocks the next step in performance, even letting engineers start stacking these things vertically. And this isn't some far-off dream either. This is coming soon. GAA is set to be the new standard for high-end chips starting around 2025.
All right, so we've got a better switch. Awesome. But modern computing, and especially AI, has created a totally different kind of problem. It's not just about how fast you can process things anymore. It's about data. A massive amount of data. I mean, modern AI models they're data monsters. They get trained on these gigantic data sets, and to do their job, they have to access that data at lightning speed. And this has created a huge traffic jam inside our computers, a problem so serious it actually has its own name. And here it is, the memory wall. Some people call it the von Neumann bottleneck. The best way to think about it is like this. Imagine you have the world's fastest chef, but they can only get one ingredient at a time from a pantry down the hall. No matter how fast that chef is, the meal is going to be slow, right? Well, that's exactly what's happening inside our chips. The processor is the chef, and it's just sitting there, starved for data from memory. So to solve this, engineers basically decided to build a data superhighway right next to the processor. The solution is called high bandwidth memory, or HBM. And instead of laying memory chips out side by side, they stack them vertically, just like a stack of pancakes. Then, and this is the crazy part, they drill thousands of tiny vertical wires called TSVs straight through the whole stack. What you end up with is an incredibly wide, super direct path for data to travel. And the results are just staggering. By 2025, the target for a 12-layer stack of HBM is 2 terabytes per second. Let that sink in. Not terabits, terabytes. To put that into perspective, that's like downloading about 50 full high-definition movies every single second. That's the kind of speed you need to feed a hungry AI. Okay, so we've redesigned the transistor. We've reinvented memory. The third revolution is all about how we put the pieces together. The whole era of having one single giant do-it-all chip is giving way to something way more modular and flexible. For years and years, the goal was always to build what's called a monolithic chip, one giant, perfect slab of silicon that did everything. The big problem with that is the bigger and more complex you make that one chip, the harder it is to manufacture without some tiny defect ruining the entire thing. It's just so expensive. So the new approach is to build with chiplets. And honestly, the best way to think of them is like specialized Lego bricks. You make a bunch of smaller, simpler chips that each do one thing really, really well, and then you just assemble them together.
And the fancy term for this approach is heterogeneous integration. It's heterogeneous because the chiplets don't all have to be the same. You can mix and match components built on totally different manufacturing processes or even from different companies, all to create a custom system that's perfectly optimized for a specific job. It's more efficient, it's cheaper, and it is so much more flexible than the old way of doing things. So let's zoom out. We have a new kind of transistor, a new memory architecture, and a whole new way to build chips. When you put all of these amazing innovations together, what does it actually, do for us? What does it enable? What it means is we've basically been handed a brand new toolkit for innovation. GAA transistors give us that fundamental boost in performance and power efficiency. 3D stacked memory like HBM just smashes right through that data bottleneck, and chiplet architectures let us combine all these pieces in new and incredibly powerful ways. And this really captures the huge paradigm shift we're living through. Progress isn't just about shrinking anymore. It's about clever, three-dimensional, modular design. It's all about creative integration, not just miniaturization. And this new toolkit is what's going to power the next great technological leaps. We're talking about AI that's powerful enough to run right on your local device, the kind of insane bandwidth we're going to need for 6G, the complex control systems for making quantum computers practical, and of course, the brains for truly autonomous cars and smarter IoT devices. Every single one of these frontiers depends on these fundamental breakthroughs we're talking about today. So it turns out the end of Moore's Law wasn't really an end at all. If anything, it was the beginning of a new, way more creative era in computing. We've moved beyond just a single road, and now we have this whole landscape of possibilities to explore. The question is no longer just how do we make it smaller? It's what's the absolute best way to build this? And with these new building blocks, the solutions we design next are going to shape our world for decades to come.